the organizers for inviting me to give this talk in Rio just before the World Cup, and then I have to go back to the US. So this is joint work with Thomas Schombeck, who's my advisor. So let's begin. It's well known that the dissipative 2D-QG equations are a good model of the 3D Navier-Stokes in the critical case. And there's been many results in the last couple decades, starting with Konstantin-Maida-Tabak, Caffarelli-Vasseur regularity, Kislev-Nassar-Wahlberg on well-postedness, and so many others. But these results, as far as we know, have been developed only for R2. And so our first question was, what about exterior domains? Exterior domain being the complement of a bounded connected set with smooth boundary. On the other hand, the exterior problem for the Navier-Stokes equations was extensively studied during the 80s, and the central theory was developed by Borchers and Miyakawa, particularly in terms of large-time behavior. And one of the main properties they showed is that there's a heat-type decay for the solutions, where the decay of the solutions is approximated by the decay of the solutions of the linear part of the equation. And in Rn, these results were obtained via Fourier Splitting, which was developed by Maria Schombeck. And basically what one does is do a separate analysis of the low and high frequencies after applying Fourier transform to the equations. And in particular, one obtains a criterion for the optimality of the decay rate. So that was important. So our next question was, is there a Fourier transform for exterior domains? So we can do this. But let's first recall the 2D-QG equations. We have U as the velocity field, theta is the temperature function, which is vectored by U, and we have a fractional dissipation represented by the fractional Laplacian with exponent alpha between 0 and 1. And we write this in terms of the square root of the Laplacian, which is the lambda operator. And there's a relation between U and theta, where the components of U are given by Riesz transforms applied to the theta function. The three main regimes that one studies are the supercritical for alpha between 0 and 1/2, the critical case for alpha equal 1/2, and the subcritical case for alpha between 1/2 and 1. So going back to my last question, there is in fact a Fourier transform for exterior domains, which was developed by Teruo Ikebe when he was doing scattering theory for the Schrödinger equation. And Michael Taylor has a very clear exposition of this in his PDE book. And we generalize his exposition to all dimensions n greater or equal to 2. N equal to 2 is harder because there's a logarithmic singularity for the fundamental solution of the Laplacian at 0. And another crucial representation we used was the Caffarelli-Silvestre harmonic extension, which allowed us to localize the fractional Laplacian and then obtain a maximum principle and some weak existence results. Okay, so the basic idea of the generalized Fourier transform. So we set up the Dirichlet exterior Laplacian in L2 of omega. It's well known that this is self-adjoint and has domain H2 intersect H01. And the basic idea is the generalized eigenfunctions of the exterior Laplacian will play the role of the complex exponentials in the classical Fourier transform over here. And the way to define the generalized eigenfunctions is as a sum of complex exponentials plus, or so-called plane waves, plus scatter waves V of xc, where V of xc solves the exterior Dirichlet problem for the Helmholtz equation with plane waves as boundary data. All right, so the main theorem is that if one starts working with C0 infinity functions to define the generalized Fourier transform, which we call phi, then we construct the adjoint map but we have to keep the C, we integrate in Rn for the adjoint map, but we have to keep the C away from 0 to accommodate for n equal 2. But in any case, that can be worked with. And the main theorem is that the map phi is a unitary map from L2 of omega into L2 of Rn, and phi star extends to its adjoint and inverse. And so we have the classical spectral representation for the fractional Laplacian using Fourier transform. And we can have an inner product and generalized Parseval's identity and so on. Okay, so as much as the phi transform is very nice, it's not as good as the classical Fourier transform. For one thing, it doesn't transform derivatives into multiplication, and it's not as nice. So a crucial thing to do to understand the mapping properties of a phi transform is to have wave number estimates, which for the generalized eigenfunctions, and which we found a method by Chandler, White, and Monk, using a combination of layer potentials to represent the scattered waves. And the trick about this is that this combination is invertible for all values of the wave number. And the main result they have there is that we can bound the L2 normal of the scattered waves on the boundary by a polynomial in the wave number. And that was very important for us for some of the arguments that we used. And so if we write down the generalized eigenfunctions like this, using the singularity potential, we have this polynomial bounds, but only for x away from the boundary of omega. And for n equal 2, we show that for all x in omega, we have this logarithmic bound in the wave number. Okay. All right, so I'm going a bit too fast. So the Caffarelli-Silvestre harmonic extension was another important tool. In Rn, Caffarelli and Silvestre set up the harmonic extension of the function u to be the function u star, which is the solution to this degenerate elliptic equation, which is it's a coupling of the Laplace equation in x in Rn and the Bessel equation for y in the positive axis. And it can be shown that this is given by the following Poisson formula. And the most important thing is that it has the Dirichlet to Neumann condition, which means when you take this fractional derivative in the y going down into Rn, what you get is the fractional Laplacian applied to the lower boundary value, which is u. And to extend this to the case of a exterior domain, we had to use a construction of Sting and Torrea, where basically they use an L2 functional calculus, which is valid for any self-adjoint operator. In their paper, they're interested in the Schrödinger equation, but this works for the exterior Laplacian also. And their main theorem in our context would be this, where basically we have the same harmonic extension problem, but we put the x variable in the exterior domain. And now this Bachner integral is the harmonic extension. And we obtain also the Dirichlet to Neumann condition. And we have a Poisson formula. And applying the phi transform in the x and adding a radiation condition in the y, you can show that this representation is unique, which is basically what Caffarelli and Silvestre did in Rn. Okay, so the dissipative 2dqg equation in omega, the framework we have for this is basically the same equation, the same quantities that I described before, but we have to set the boundary value of the temperature to be 0 on the lateral boundary, which would be this condition over here. And the key thing here is that I don't know of any proof for generalized exterior domains to show that the Riesz transforms are bounded in LP from LP to LP for all P between 1 and infinity. I have some results for certain P's, but these are involved with certain estimates for the heat kernel that I'm still working on and so on. But we just assume there's some kind of Riesz transform or some operators that would relate the u and the theta in this way. So one standard way to get existence for global weak solutions would be to extend what one has for bounded domains, which was done by Resnick. And basically one extend this by approximating over bounded subdomains and then doing a diagonalization argument. That's pretty easy. We wanted to sort of emulate the classical approach for existence in Rn for the 2dqg, but we didn't really get very far. We actually need a much more accurate way of representing the Fourier transform or the spectral properties of the Laplacian in that way. But in any case, what we had was if we start with a perturbation of the equation for the mild solutions of the 2dqg, we basically using the divergence free condition, we can construct this operator LS, which is sort of the semigroup with the divergence operator here. And then using the wave number estimates and the exterior or the Helmholtz decomposition in LP for the exterior domain, we have that it's bounded in this operator LS is bounded in L2, and this H beta would be the Sobolev basis for the exterior Laplacian in a way. And we can show the continuity of this operator in H beta using these estimates for P between 1 and n. Okay. How much time do I have? 5 more minutes? Okay. Okay, so so the basic argument was with this lemma, we can construct the typical bilinear form and show that it's continuous in these spaces, which are sort of the analogous spaces to the classical case, and then apply the fixed point theorem by Cato, which is usually applied Cato, and show the local existence and uniqueness of the perturbed solutions. We also have the energy estimate, the energy inequality for the perturbed solutions, and we have a uniform bound here, which after extending this with Gronwald's lemma and so on, we can apply the Aubin-Lyon's lemma to get a limit in the space L to 0 infinity H alpha. But these would be far from any kind of unique solutions or anything like that. So it's a weak argument. We wanted to see what happened there. And I think I'm arriving at my last slide, yeah. All right, so these are the decay results we obtained. This is the positivity lemma, which was done by Antonio Cordova, and Diego Cordova. And basically, this lemma we can prove with the Caffarelli-Silvestri extension just by applying Gauss divergence theorem and using the vanishing in the boundary. But it's pretty standard. I'm not sure if I should say it's easier, but using the Caffarelli-Silvestri harmonic extension is pretty simple. And then this maximum principle is exactly the same as in Rn. And then we can apply the Fourier splitting. Just as in the standard way, the only thing is that we have to have a control of the L2 norma of the generalized eigenfunctions. And that basically one does by controlling the L2 norm over balls over which one integrates in the frequency variable. This is an exercise in Michael Taylor's book, but the argument is pretty much the same. And I think I went too fast. That would be all I would say. Yes. Thank you very much.